Hello everyone. In this lecture, we will discuss about the utility of various LLMs, available LLMs for analysis of synchronous FIFO design. In fact, the GPTs, that is generative pre-trained transformers, are a type of large language models which enable us to generate software codes or to communicate like a conversational AI type of requirements. So LLMs have been used for a variety of purposes. We can use it for understanding a concept, or we can use it for an analysis, or we can use it for some interpretations. Just like a technical conversational tool, we can use it. So I start with basic synchronous FIFO structure because the during the last class we discussed about the existing LLMs that have been utilized for the Verilog and System Verilog RTL development. In fact, that is our focus. How can we utilize the LLM effectively for generation of RTL code and test bench code is our attention right now. Therefore, the different types of LLMs like a Claude on Sonnet LLM, and then we have the Chat GPTs, then we have the Gemini, which is of Google. So all these things, all these LLMs, all these available LLMs have been utilized extensively for the for analysis of their capability to generate easy, medium, and complex level RTL codes and test benches. Therefore, so we discussed a bit about the basic architecture of the LLM utility. I mean, this large language models, like we have encoder, decoder structure, and training aspects. So those things. So now I will discuss with an example on how to utilize the LLM. How to utilize the LLMs for generation of RTL code has to be explored in our laboratory experiment. So, considering the laboratory requirement, I will begin this particular discussion right now. So, today's session will focus on how to generate the synchronous FIFO design. We are going to write the synchronous FIFO design through our understanding of the concept. Then we will discuss about how to modify the synchronous FIFO design with the LLM. Then how to insert bug in the LLM and ask the LLM to modify. Then given a partial code of the FIFO, how the different LLMs are capable of generating the code, right? So all these things are now going to be checked with the a test bench that has been developed by us. So before beginning that, we will discuss about we will explore what is a FFO. Okay, as a FIFO. In fact, FIFO stands for first in, first out. It is a kind of digital memory. It's a kind of digital memory. Therefore, we have all the operations, right? So all the operations are happening on a single clock domain. If you think about memory, we have static RAM, dynamic RAM, etc. like that. But FIFO is something different from that, right? In the static memory, let us take. So we discussed a static memory design also. So in the static memory, we have a clock reset, we have a write enable or read enable. So write enable is a single bit based on the write enable's logic status, whether it is high or low. We can decide whether it represents the write operation or read operation. Then we have address, data in and data out. So when we decide to write something on the memory, then we will point some address to that. We'll give some address and then we will give some data so that it will be stored in an internal memory. And when we want to read the data, we will give the same address and write enable maybe 0. Let us take write enable equal to 1 is write enable 1, write enable equal to 0 is reading. So in that case, when write enable is 1 and address is given and data is given, then internally it will store the data. And when we want to read the data from the memory, then write enable can be moved to 0, so that when we give the address, the data in the particular address can be read back. This is the basic structure of your static RAM. But now what is the difference between static RAM and FIFO? FIFO does not have any address. FIFO does not have any address, but it will have a fixed entry or fixed depth, right? It is called first in first out. It's a kind of queue. Okay, so queue depth can be specified. So what happens when we start writing the data, and at a particular clock frequency, the data will be written there. And when we want to read the data will be read in a sequential manner, right? So whatever we are writing 1, 2, 3, 4, 5, the same thing will be read in the same order. That is why it is called as first in first out. So remember, the difference between static RAM and FIFO is static RAM has address, a specific address, and FIFO does not have any address. You can read the data from random locations in static memory, but it is not possible in the case of FIFO. You have to read the data in a sequential manner itself. So FIFO is of two types. One is called synchronous FIFO, another one is asynchronous FIFO. In synchronous FIFO, read and write operations are happening with respect to same clock frequency. You have a single clock only in the synchronous FIFO, whereas in the asynchronous FIFO, you have two clocks, read clock and write clock. In the asynchronous FIFO, you have two clocks, synchronous, read clock and write clock, and there are, it is being used as an internal structure, interconnect structure. You want to connect, you want to pass data from one end to other end. FIFO is a good interconnect structure wherein you can pass data from one end to other end by keeping the FIFO inside. Accordingly, so basically when the FIFO finds its utility very well when the source end and destination end are operating at different clock frequencies, and you want to pass the data without any miss, right, without any loss. You want to pass data from one end to other end without any loss. In that case, FIFO is very helpful, because your source block is operating at some frequency and destination block is operating at some frequency. So in that case, when you try to pass the data from high frequency to low frequency, then high frequency block can transmit data at higher rate, whereas low frequency block has very less sampling rate. Because of that, it can miss the data. Similarly, if you pass the data from low frequency end to high frequency end, then the possibility of malformed data entry is more in the case of passing data from low frequency to high frequencies. To avoid that, FIFO is being used as an interconnect structure to communicate the data effectively between two ends. Okay, so this is one response from Claude Sonnet. So it gives the details about FIFO like this. So I thought that it is good to know that through this particular response of the Claude. Okay, so synchronous FIFO is a digital memory buffer where all operations occur in a single clock domain, as I was telling you. FIFO is an interconnect structure, acts as a bridge to communicate data between two different blocks. FIFO is operating at single clock for both reading and writing. Synchronous FIFO especially. Asynchronous FIFO uses two clocks, one for read clock, another for writing. It's a fundamental building block in digital design, serving as a queue that maintains the order of the data. Order of the data is important because we don't have any address lines in this FIFO. Therefore, the order in which we are writing the data is going to be followed for reading as well. The first data written is the first data read. Key characteristics: single clock domain, All operations read and write are synchronized to the same clock, simplifying timing analysis. Sequential data access. Data enters and leave in the same order, first in, first out. Pointers management, we have two pointers. One is called the write pointer and read pointer. So these pointers are not available in the static RAM. They are not available because here we have to manage the reading and writing effectively. Therefore, we have to know when the queue is full, when the FIFO buffer is full, when the FIFO buffer is empty. Okay, so when the FIFO buffer is full, it is not capable of following the next data. If you are writing the data one by one before reading it, then there is a possibility of data loss. To avoid the data loss, we are having two indicators. One is called full and empty. Write pointer indicates where the next data will be written. The write pointer is managing the depth of the FIFO. Okay, when you are writing the data internally, what happens once you are written the data, write pointer moves to the next location so that the data will be written in the next location. Read pointer indicates where the next data will be read from. Both pointers increment after their respective operations. Status flags. So there are two things. One is called pointer, another one is called status flag. Synchronous FIFO has two pointers. One is called write pointer, another one is read pointer. We have two status flags. One is called empty, another one is called full. Asserted when read pointer equals a write pointer. Empty. When you can say that empty, that means when you have written the data in all the locations or little lesser location, it is not mandatory that the reading can happen only after writing in all the location. So how are you going to control the reading and writing? We are having some input signals called read request and write request. If you say write request, the data will be written. You say read request, you can read the data. So both are manageable. We have empty status flag. It is asserted when read pointer equals the write pointer. Okay, and full typically detected when pointers have wrapper. That is, MSB bits differ while address bits match. See, if you say the full, okay, if you have written the data in all the locations, then the buffer is full. Okay, so when it is full, then what you should do is we have to read the data so that the buffer is ready for the next round of reading and writing. Optional, almost full, almost empty, half full. So these things are only optional. Internal structure. A synchronous FIFO typically consists of a memory array, storage for data elements, often implemented as a RAM, so that they are internally managed. Okay. With respect to interface of the synchronous FIFO, you have a clock, you have a reset, you have a write request, you have a read request. They are inputs, and then we have data in, that is also the input. Then we have empty flag, null flag. Then we have the data out. You don't have any address lines in this. There is no address line because random reading and writing is not possible in the case of FIFO. Its purpose is not like that. For randomly reading and writing, you can use either static RAM or DRAM like that. But as FIFO is being used as an internal interconnect component, it is important for so it is important for us to utilize the FIFO effectively whenever a kind of queue kind of operation is required to be performed. So pointer register, track read and write positions, control logic, manages pointer updates and generates status flags, right? Based on the status flag, control operation. So reading operation, writing operation, then pointer control. These are the three things to be managed with respect to FIFO design. Operation principles. Write operation. Check if FIFO is not full. Check if FIFO is full, then we cannot write. If FIFO is not full, we can write it. So empty and full conditions are completely different. Okay. When the FIFO is not full, we can write it. Write data to the location pointed by right pointer, increment right pointer. Then coming to read operation, check if FIFO is not empty. So if FIFO is not full, we can write it. If FIFO is not empty, we can read it. If it is empty, then no data is available to be read. That is the underlying meaning. Read data from location pointed by the read pointer. Okay, here we are writing the data to the location pointed by right pointer. Here reading the data from the location pointed by the read pointer. Increment read pointer, here increment right pointer. So write operation, read operation. Three things are there. One is pointer management, right pointer and read pointer management. There are conditions we have to write. There are, because we are using the status of right pointer in write operation, read pointer in read operation. Okay, when we can write only if FIFO is not full. That means if if full flag is not 1, if full flag 1 means FIFO is full, so you cannot write it. If full flag is equal to 0, you can write it. If empty flag is equal to 0, you can read. Empty flag 0 status means you have some data to be read. You have some data to be read. So if you think about a particular series, if you have data to be written in 8 locations, let us say, you will write the data in subsequent locations. Sequentially, you will write the data 1, 2, 3, 4, 5, 6, 7, 8. At the end of 8 data writing, then full flag becomes 1. Now it is turn for us to read the data. Now once you are reading the data in location 1, 2, 3, 4, 5, 6, 7, 8, because I told you that random reading and writing is not possible with the basic FIFO structures. There may be possibility to add something, but that is not widely used. We don't have address. In fact, the purpose is different. Writing sequentially to a particular depth of the data and then try to read it. That is what happening with respect to FIFO. Therefore, once the full flag becomes 1, you are going to read the data. Finally, you are reading the data from all the 8 locations. So then what happens? Now empty flag becomes 1. Okay. So this is how the cycle happens. Once you have written all the data, full flag becomes 1. Once you have read all the data, the empty flag becomes. So what is the indication of empty flag 1? Empty flag equal to 1 means now the FIFO is empty. You can now start writing the data. As the FIFO is used as an interconnect structure, it is important for us to do the reading and writing with respect to same clock frequency, so that it's called synchronous FIFO, right? Imagine that the data has to be passed from end 1 to end 2, both are operating under same clock frequency, so the data loss will not be there. If you feel that both are operating at different frequencies, then we have to design asynchronous FIFO. Then you have pointer implementation. For a FIFO depth of 2 power n, pointers are typically n plus 1 bits wide. Okay, this is important. So if you are going to write data in n locations, okay, then the pointer size is going to be n plus 1. There is a purpose for this because we are going to control the read pointer and write pointer statuses based on this n plus 1 bits. So if the FIFO depth is 16, then the pointer should be 17. If the FIFO depth is 4, then the pointer should be of 3 bits or something like that. So 2 power n is that. So if you have 2 power 8 bits as the FIFO depth, then you have 9 bits as the width of the pointer, read pointer. Both read pointer and write pointer should be of same size. Extra bit is used to wrap around detection. Wraparound detection means especially for pointer logical operation, that you will know how the pointers are calculated. The lower n bits address the memory location. That is important. Lower n bit address the memory location. The last The MSB bit is used to control the especially the full condition. Simplicity. So easier to implement than asynchronous FIFOs. Deterministic timing. All operations are synchronized to single clock. No metastability issue. No clock domain crossing concern. So clock domain crossing concern is a big issue in the case of asynchronous FIFOs. The rate matching between modules operating at different speeds in the same clock domain. Command buffering in processors and controllers. Packet processing in networking applications. Pipeline stages to improve throughput in pipeline designs. So design considerations here, you have depth sizing must be sufficient for the application's requirement. Flag generation critical for proper flow control, reset strategy, proper initialization of pointers and flags. Performance, read and write can typically happen simultaneously because we have a single clock. So synchronous FIFOs are essential components in digital systems where data buffering is needed within a single clock domain, providing clean interface between modules operating at different rates. Now, moving on to the basic RTL code, so it's a system Verilog code, right? So this is synchronous FIFO without any parameterization. You can think about the parameterization later. So this is synchronous FIFO with 8-bit depth. That means synchronous FIFO with 8 entries. It can write data in 8 locations. Each data is of 4 bits width. So we have these following interface. We have inputs, clock, reset underscore n. So this should be synchronous reset that has been implemented here. Then we have write request, write underscore request, read underscore request. Write underscore request is used for writing the data. Read underscore request is for reading the data. Then we have 4-bit width. The data in is of 4-bit width. Then we have output full flag, empty flag. Then we have the data underscore out. So this is the data in and the data underscore out. Now, so we are not using any reg or logic for the full and empty because they are going to be they are going to be utilized based on combinational logic. Their conditions are going to be operated based on a combinational logic. Then we have logic memory. So this is for internal. This is for internal storage. Okay, like our SRAM, where we have internal storage, we will have this thing also. The FIFO depth is FIFO depth is 8 in this case. Okay. So because we have mem of 7:0, so each we have 8 locations in this internal memory with each location capable of storing 4 bits of data. So data in is 4-bit, data out is 4-bit. Similarly, internal memory width is also 4 bits. Then you have write pointer and read pointer. So okay, so size equal to FIFO depth plus 1. Okay. So here we have the FIFO depth is 8. So if we have 8-bit depth, so 8 location depth, then you need to have read pointer and write pointer as 9. Okay. So it should be, in fact, it can be understood like this. So FIFO depth is 8. So it is 2 power, so 2 power 3. So we say 2 power n. Okay. So 2 power n. So the FIFO, the size should be equal to n plus 1. That's a better understanding. If you fix the FIFO depth as 8, for example, if you say 7 or something like that, so you can write in 8 location. Actually, it is related to the number of bits that you are allotting. Okay. So you are allotting 3 bits for the FIFO depth representation. 3 bit means you can write in 8 locations. So if the FIFO depth is represented in 3 bits, then the read pointer and write pointer width should be of 4 bits. Okay, that is the understanding. If you are using 4 bits as the FIFO depth representation, then read pointer and write pointer should be 5 bits. That is the understanding. So 2 power 3 because it has 8 locations, so it can be represented as 2 power n where n is equal to 3. Since read pointer and write pointer are n plus 1 bits, so you are going to have 4 as the read pointer and write pointer bits. Now empty and full condition has to be assigned. Empty means when read pointer and write pointer are equal, it represents the empty. When read pointer and write pointer are equal, it represents the empty condition. Okay. So that means it may be two cases. One is read pointer equal to 1 and write pointer equal to 1, or read pointer equal to 0 and write pointer equal to 0. So most of the cases that is good. So that means the empty represents that we can write the data into the FIFO. Then full condition. So what is the full condition, right? Then read pointer of 2 colon 0 equal to write pointer of 2 colon 0. So now read pointer and write pointer are of 4 bit width. Now we are discarding the MSB and we are taking the other bits other than the MSB. So that means the number of locations of FIFO are addressed here. The first condition is when write pointer of 2 colon 0 is equal to read pointer of 2 colon 0. For example, you have this is representing the full condition that is helpful for writing the data. Yeah. So for writing the data, we are going to use the full condition. We are going to check whether it is not full, then only we can write the data. When write pointer of 3 not equal to read pointer of 3. That means one typical cases I can say. So this can be like this. So 100, right? So 100 is right pointer and 000 is read pointer. This is one condition. Another condition could be 1111 right pointer and then we have 0111 read pointer. So empty condition is whenever read pointer is equal to write pointer, then it is called empty. That means what does it mean? When you are writing in 3 locations and you have read the data in 3 locations, both read pointer and write pointer will be equal. Read pointer will be equal to 0, write pointer will also be equal to 0. Equal to 3, both are equal to 3. Right? When write pointer is 3 and read pointer is 0, then it is not empty because you have written the data but you have not read it. You have to write the data and you have to read the data. The status of them equal. Okay, they can be 1 1 2 2 3 3 4 4 like that. If write pointer is 4 and read pointer is 4, that means you have written data in 4 locations and you have read data from the all locations. Okay, so in that case what happens? Now FIFO is empty. You have to write the data, new data. A new data has to be written. That is the meaning. In full condition means you have written data in all the locations. So that is what here this condition represents. When write pointer of 2 colon 0 equal to read pointer of 2 colon 0. Okay, and write pointer of 3 not equal to read pointer of 3. That means you have now you have written in all the data. You have written the data in all the locations. Now you have to read it. That is the meaning of this. Data write in FIFO. Okay, always at passage clock. If reset equal to 0. So this is a synchronous clock because based on the clock edge the reset works. So here we are clearing the memory of right pointer, memory of right pointer. Okay, so this is controlled only in the right operation, because right operation is controlling the memory. The right pointer is driving the memory, driving the internal memory. Read operation is only reading the status. Else, if write request equal to 1, when are you going to write the data into the FIFO? Only if write request is equal to 1. When the write request is equal to 1 and it is not full, you can write the data. That means if full is equal to 0, write a request equal to 1. Then only you can write the data. So in that it's similar to SRAM writing. So mem of some location, some there you in the SRAM you are going to have mem of address, because you are specifying the address and you are specifying in what address the data has to be written. But here it is not like that. Address input line is not available. Therefore, based on the right pointer status, the writing will happen. Mem of right pointer of 2:0, because 2:0 is a represents a number of right pointer locations. Only 8 locations are going to be utilized now. Right pointer of 2:0 equal to data underscore in. Then whatever the data input is available, that will be written in the right pointer location. Now once you have written the data in the particular location, right pointer gets incremented by 1. Right pointer gets incremented by 1. So it is simple. We are clearing the memory, internal memory, when reset is 0. Then we are checking whether write request is 1, and if it is not full, we are going to write the data. Mem of the right pointer location equal to data in, right pointer gets incremented. Then data reading in FIFO. Now what is the condition for reading? So now we are keeping the data out equal to 0, read pointer equal to 0. Else if read request is equal to 1. When the read request is equal to 1 and it is not empty. If it is not empty. Not empty means if you can read the data from the FIFO, new data, if you have to read it, then empty has to be 0. Okay, then only you can read the data. If the empty 1, then you cannot read the data. If empty equal to 1, then it represents there is no data to be read. Therefore, for writing the data, full flag should be equal to 0. For reading the data, empty flag should be equal to 0. Then read pointer gets incremented by 1. Data out equal to mem of r point read pointer of 2:0. Okay. Now for checking this, I have written a small test bench. So this one is synchronous FIFO.sv. Um, synchronous FIFO.sv. So now time scale, so this is a TB to check the synchronous FIFO, reg clock, clock reset, write request, read request in data in all are of reg data type. Here it is wire, full wire empty, wire of 3:0 data underscore out. These should be wire because output should be wire. This can be reg or logic data type also. So sync FIFO instantiation, I am using the same signal names here as well, therefore no change, just to map them. So the order is based on the name, mapping by name. Clock reset n, reset underscore n, write request, read request, data in, full empty, and data underscore out. So we are beginning the clock. So this is going to be 10 nanosecond clock with 5 nanosecond on, 5 nanosecond off. First, initially, I am making reset equal to 0. See, we have only one reset. When reset is 0, it clears the read pointer and write pointer internal memory. Reset underscore n equal to 0, write request 0, read request 0. Once that is done, next in the positive edge of the clock, we are going to use this. We are making the reset equal to 1, then only reading or writing is possible. Now, first operation is writing. Write request equal to 1. Repeat of, I would say that repeat of 8, repeat of 8, repeat of here I can keep it as 10, repeat of 8, write request equal to 1, writing data, random data I am taking as data in, then I am displaying the data, read request, write request, data in, empty and full. Then at the neck edge of the clock, I'm just manage giving because if you are reading during the same positive edge of the clock, then it may the reading or writing may not be proper. So the test bench I'm using at neck edge clock for operating it, or you can use the delay also. But it is advisable if you are operating everything with the clock edge, you can operate with the clock edge also. Okay, this is a small block for used for a write operation. Now I am not writing and reading consequently, because many tests can be generated based on this, writing partially, reading partially, like that. So now I am going to read the data. So in this write condition, what happens once you have written all the data, then full flag becomes 1. That is the condition we have to check. And the FIFO read operation, then write request equal to 0, read request equal to 1, then we are going to just read the data, that's all. We are going to read the data. Reading data happens only if you keep the read request equal to 1, that's all. There is no need to give any address at all. Then I'm finishing this. Okay, so now let us try to execute this. Yeah, so now I have run the test bench. You can see this. So now what happens is write request is 1 for 8 clock cycles. So first data 9403 81230. So these are the 8 data that have been written into the FIFO memory. So we have written the data, we have generated data in, and we have written into the memory. And now empty is 1, that's at the start of the FIFO writing. So once it has written the data in all the location, that is FIFO depth is 8 in this case. So once the data has been written in all the location, now the full flag becomes 1. Here you can see this, the full flag becomes 1. So once the full flag becomes 1 based on the test, right? So you can partially read and write, that is also possible. For example, 3 locations read, 3 locations write, that is also possible. In that case, see, the FIFO is not all, not like you can write in all the locations, then only you can read. It's not like that. If you want to read and write and manage data in between also, you can do it. But at the same time, the full and empty may not be 1 or 0. Reading and writing is always allowed. Now, as per this particular test bench, I will write data in all the 8 locations. Then I have to read the data. When you are reading the data, data appears at data underscore out for further processing, because it's an interconnect structure. FIFO is an interconnect structure. It has to connect 2 blocks. Okay, so you have written the data in all the things, and now once the writing happens, data has to be read. So during the writing phase, what happens? The data one by one comes through the positive edge of the clock through the data underscore out. We have 9403 81230. So the same order, that is why it is called as first in first out. First data was 9, here also first data. So whichever data has been stored in first in order will be first out. The same order it will come, because we don't have any address specific location. For example, randomly you can read it. Way in which the order in which you are writing, the same order you can read it. 9403 812 30. So after reading all the data, what happens? Empty flag becomes 1. Empty flag becomes 1. And now so there are some cases empty flag is 1, and for writing we are not checking empty flag. Okay, we are checking only full flag. So obviously even if empty flag is equal to 1, you can write the data. Okay, that's not a issue there. So what you have to understand here is, after writing in all the location, when the write pointer becomes 8, the full becomes 1. When the read pointers become 8, empty flag becomes 1. Okay, now moving on to the code modification, LLM uh, analysis. Okay, so here I use first I use uh, the Claude for this. Okay, so here I say I'm giving a partial code of synchronous FIFO. Can you complete the RTL code in system? So this has been done with EduArena. So here in this direct you can choose the LLMs. There are many LLMs available. So I have chosen Claude, Gemini, GPT can be chosen, or O4 can be. Both are OpenAI, but recent thing is GPT-5. So I encourage you to use GPT-5, Gemini 2.5, then Claude 3.7. These are the three things we can make use of this. I'm giving a partial code. This is called prompt in the LLM. I'm giving a partial code of synchronous FIFO. Can you complete the RTL code in system? So module sync FIFO, whatever I have written on my own. So I gave only this particular code section. I gave the interface and the internal memory with empty and full condition. Then it has written the code, and gave me back. Here is a completed RTL code. So sync FIFO, so partial code I gave only up to this. So it has completed write pointer logic and read pointer logic. So this code, now we have to take this. So this code was taken, and here you can see this, the same code, sync FIFO Claude. So this was written with Claude LLM. I gave only up to this, up to 14 line, right? Our initial code. So now it has written the right pointer logic. What is the difference? Now I did not specify anything about the reset. So the code that I wrote was based on synchronous reset, but now it has written is a asynchronous reset. It has assumed on its own. Suppose you want to right. So these are the things we have to understand. How far we are properly giving the prompt. We'll discuss about that later also. I have not given any instruction that it should be a synchronous reset or asynchronous reset, but it has assumed it as asynchronous reset. So right pointer is now asynchronous reset, right pointer becomes 0, and then now if you compare the condition, both the condition, when write request is 1 and not full, then writing happens. When the read request is 1 and not empty, reading happens. It is same. It is very similar to what I have written here. Only the difference between this code and that code is, here I have used synchronous reset, and the code generated by Claude is using the asynchronous reset. Now let us check this code. Here include sync FIFO, and so what I'm doing is, now I am checking the code generated by LLM with the same TB that I have written. That is important. For the same specification, whatever be the code generated by you, your TB is going to respond in some way. The same way we have to check that also. Yeah. So now I have changed the code in the TB only. Okay, I have included sync FIFO Claude, and the instantiation, instead of sync FIFO, I use sync FIFO Claude. Now I am checking the test bench. So the same response, right? So 9403 81230. Then after that full flag becomes 1. Now here empty flag becomes 1. It is very perfect. The code generated by Claude LLM is perfect. So synchronous FIFO is perfect. Now moving on to next. So now I was telling you three things. One is generation of completion of the code from the partial code. Second one is bug. Third one is modification. Okay. So now, so here also I use this Claude. Okay. The functionality of the synchronous FIFO is not correct. The functionality of the synchronous FIFO is not correct. It produces outputs wrongly. Can you identify the bug and correct the RTL? The functionality of the synchronous FIFO is not correct. It produces outputs wrongly. Can you identify the bug and correct RTL? So what I have done here, I have given some bug. I have introduced some bug here. So in laboratory experiment also, you have to introduce some bug in the RTL code and check whether LLM is capable of generating it properly, correcting it or not. Now, assign empty, right pointer is not equal to read pointer, and now it is a different condition. For empty condition, right pointer should be equal to read pointer, and for full condition, here right pointer of 3 not equal to read pointer. So there are two logic mistakes here. Here this should be double equal to, here this should be not equal. These are the two bugs I have introduced. Because of that, it will the behavior will be chaotic and will be a little bit deviated on, because the entire before writing reading happens based on the empty and full flags. So now the conditions are wrong here. So write and read remains the same, that logic remains the same. Yeah, now this is a response. So this was checked with Gemini 2.5 Flash LLM. So that was checked with Claude. The partial, the full code generation from partial code generation was handled with Claude. Now I used a different GPT, that is Gemini. The provided synchronous FIFO RTL code has several bugs that led to incorrect functionality, especially regarding empty and full state. So it has identified the error actually. It has identified that the error is in empty and full status. So incorrect empty assignment. Original is assign empty equal to right pointer not equal to read pointer. That should be correction. Correction should be assign empty equal to when right pointer is equal to read pointer. Similarly, incorrect full assignment. Okay. So this condition is true when right pointer and read pointer are identical, including the MSB, which also makes empty true. For an 8 entry FIFO, right pointer and read pointer are 4 bit. This is understandable. The lower 3 bits are used for memory addressing, so they should be checked. It is correct. That condition is correct. Among two conditions, this second condition of checking whether right pointer LSBs of right pointer are equal to read pointer, that is correct. But when right pointer of MSB of right pointer E should not be equal to read pointer, that is the condition. When MSB of right pointer is not equal to read pointer, so that's what they have corrected here. This is a corrected code. When MSB of right pointer is not equal to read pointer, and then when the LSBs are equal, okay, this is the common condition that has to be used. Okay, so now this is generated by the Gemini. Okay, let us see this code actually. Okay, so now output full and output empty. Okay. Okay, so now it has corrected it. Let us not check this. Only two conditions it has corrected. Another one, can you modify the following RTL code to support 32 as the maximum depth of the synchronous FIFO? This is the third category in RTL handling with LLM. This is the code modification. First one was partial code completion. Second one is bug identification. Third one is RTL modification. Now I want LLM to modify the FIFO depth from 8 to 32. So that means you are going to have 32 locations there. So I gave the code as the code that I have written, which is of 8-bit depth. So this was also tested with Gemini. To modify the synchronous FIFO support of maximum depth to, we need to adjust the following: memory size. Memory array needs to be declared to hold 32 entries. So pointer width. So full condition, empty condition, all these things are correct. So now they have generated with some parameters. Okay. So now again I am asking, I don't want any parameters. Can you modify the following RTL code to support 32 as the maximum depth of synchronous FIFO? So I did not mention that you add parameter or don't add parameter. So here is what you have to understand. You have to give the instruction properly. If you don't specify anything, it will assume something and it will give it. Maybe right or wrong. Don't add any parameters. So I modified the prompt. So it gives me like this. So to modify synchronous FIFO to support a maximum depth of 32 without adding parameters, we need to hard code the changes for the memory size. So what happens is, it has generated one particular code, right, with uh, yeah, sorry, here this is a code. So what happens is data width remains the same. That is not, so it means the width of single location is not going to change, only the vertical depth is going to change. So what is the condition, what is the modification here? Instead of okay, instead of 7 colon 0 in the memory, it is going to be 31 colon 0, 31 colon 0, and the pointers also, read pointer and write pointer, are also going to be changed. They are going to be 5 colons, okay, 5 colon 0. Now coming to this, other remains the same, other remains the same. Similarly this condition is also different. Now look at this particular code. Let us take this particular code. They are keeping output logic full and output logic empty. Output logic full and output logic empty. So this is a code generated by Gemini. So output logic full, output logic empty. So now I am going to run this with this TB. Synchronous FIFO is the Gemini. This is given the modified code Gemini, right? So other things remain the same. So now I am running this. So now observe this. What happens? There is a error that is coming here. Why? Because code is little bit different here. Error, variable empty, cannot be driven by a primitive or continuous assignment. Okay, what does it say is, here in the code, the full and empty are combinational logic segments. Empty and full are based on continuous assignment statement. So it says if you use logic there, it is wrong. So in earlier codes, logic was not present. So now the code generated by Gemini has to be adjusted manually. So this is a challenge now. Okay. So now Icarus is not allowing us to run that. Now I am running this EVB test. Okay. Yeah. So this is good. Okay. So here I did not change the test bench, in fact, for whole bit. Now just I am running with just 8 bits. So 9403 81230. So full flag is not becoming 1 here. Immediately I want to read the data. So this is a condition. Even if empty full flag is not 1, you can read the data. Okay. So again same order it has come. So finally after reading all the data, empty flag becomes 1. Okay. Now if you want to modify the TB in such a way that you want to read and write from all the locations, maybe you have to adjust some parameters. So you can say that repeat of 32, and this can be repeat of 34, just to check whether the empty flag is becoming 1. Now this thing also has to be adjusted, because 320 plus 320, so 640, I will make it as 700 nanoseconds. So and run this again. Yeah, this is good. So 94, so this has written 9403. So some random data are coming, random data are written because I use random $u random underscore range. So after writing in all the 32-bit locations, now full flag becomes 1. This is a code generated by the LLM. So finally the empty flag, the full flag becomes 1 after writing the all data, final data 38. So after reading all the 38, so data is also absolutely same here, 11.9, absolutely same. So we are writing data in 32 location, reading data in all the 32 location. Okay. So this is how we have to understand the LLMs. First, initially synchronous FIFO with our own design. Then three things we tested. We used Claude and Gemini mostly here. So you can also point out this. So the mistakes. Okay. So here I pointed out the some of the mistakes. Like yeah. So the above code should not have logic for full and empty signal. It gives following error in Keras simulator. So after that, yeah, it says it modified this. It removed the output wire full instead of logic. It changed them as wire and wire full, wire empty. And in fact, it is working there. So both Gemini and Claude are capable of generating good code as far as this particular example is concerned. For complex designs, it may be something different. So we bug identification, then RTL modification, then generation of full code from the partial code. So all these things we have uh, uh, checked with these two LLMs. Thank you.